today we will discuss about the moment of inertia. Moment of inertia. So as we know that inertia of a body is the nature to resist the change in it, or moment of inertia is the resistivity to the circular motion. Resistivity to the circular motion. So moment of inertia of two type. Number one is area moment of inertia. Area moment of inertia, and second is mass moment of inertia. So in area moment of inertia, we consider area of a two-dimensional shape, and here we consider the mass of the body or three-dimensional body. So as in the centroid, we consider here only the area, or area moment of inertia is only for the two-dimensional figures, whereas mass moment of inertia is for three-dimensional bodies, as in the case of center of gravity. So here mass is considered and here area is considered. So now first of all we take area moment of inertia. So in this area moment of inertia is second moment of area about a reference line considered. Second moment of area about a reference line considered. It means two times moment. Two times moment of area. If A is the area and R is the distance from reference line. So first moment, suppose this is area A and this is the reference line, and from this reference line the distance is R. So first moment of area about this reference line, first moment of this area about this reference line is AR, A into R, and second time moment or second moment of same area is AR into again multiplied by R. So second moment is first moment of the first moment. So AR into R. So this is AR square. Suppose this is reference line is y-axis. So this will be IYY. So this is the second moment of area. So now if there is a area A, this area is A, and from its centroid these are the axes along, this is along x-axis and this is along y axis. So this is the centroid of this area A. This is a regular area, capital A, and this is the centroid of this area, and these are the axes passing through the centroid. So these are called as centroidal axis. Centroidal axes. These both are called as centroidal axis. This is along y-axis and this is along x-axis. So these both are called as centroidal axis. Now we consider a small elemental area within this area. This is dA, and this area dA is at a distance x from y-axis and at a distance y from x-axis. This dA is at a distance y from x-axis and at x from y-axis. So now the area moment of inertia of this area about y-axis or x-axis will be equal to the second moment of this area about x-axis or y-axis. So now if we find about x-axis, so this will be denoted by ixx, and this will be equal to dA into y square, second moment of area. This is the second moment of this area. Now for this total area, it can be integrated into the whole area. So integration sign. So this is the moment of area moment of inertia about x-axis of this area A. So this is ixx. Ixx is denoted about x-axis. Area moment of inertia of this area, total area about x-axis, is denoted by integration of dA into y. Similarly, Iyy is equal to second moment of area about y-axis. So the distance is x and its square will give the integration of it will give the total area moment of inertia of this area about y-axis. So it is denoted by Iyy and it is denoted by Ixx, or on integrating this will give the total moment of area moment of inertia about x-axis and y-axis. Now next is the polar moment of inertia. Polar moment of inertia or moment inertia about z-axis. So z-axis is like this. This is z-axis. So this is z-axis is perpendicular to x-axis and y-axis. So this z-axis is perpendicular to both x-axis and y-axis. So for this, if we draw a figure like this, so this is the x-axis and this is y-axis and this is the area dA. So this distance is y and this distance is x. Now this, if this is z axis, so from this z axis, the distance is perpendicular distance is this. So suppose this is z. So from this is also equal to x. So we can say z square is equal to x square plus y square. Z square is equal to x square plus y square. So now if we find Ixx is equal to dA into y square, Iyy is equal to dA into x square, and Izz can be written as equal to dA into z square, dA into z square. So by these three equations and this equation, from this equation, we can say that dA into z square is equal to dA into x square plus dA into y square. If we multiply this equation by dA, so dA into z square is equal to dA into x square plus dA into y square. So this Izz equal to Iyy plus Ixx. So this is called Izz is equal to Ixx plus Iyy. So from this is a relation, and from this relation we can find out the area moment of inertia about z axis. So this is called as perpendicular axis theorem. This is called as perpendicular axis theorem. This is called as perpendicular axis theorem because all the axes are mutually perpendicular, or it is Izz is polar moment of inertia. So to find the polar moment of inertia, we can add up the moment of inertia about x-axis and y-axis. So by adding these two values directly, we can find out the Izz, and this is called as polar moment of inertia. Polar moment of inertia. It is called as polar moment of inertia. Now the parallel axis theorem. So by this parallel axis theorem, we can transfer the moment of inertia about any area to a parallel line, to this centroidal axis, to these centroidal axes. So for this is an area, and these are the centroidal axes. These both are the centroidal axes. Now the moment of inertia of this area about x-axis will be denoted by Ixx, Ixx will be the moment of inertia of this area about x-axis, and Iyy will be the moment of inertia about y-axis. So now there is a parallel line. This is a parallel line to the centroidal axis along x-axis. So this is the centroidal axis along x-axis. To this centroidal axis, this is a parallel line named as AB. This is a parallel line named as AB. And the distance between these two lines is denoted by y, capital Y. So the moment of inertia about this parallel line by this parallel axis theorem will be equal to IAB, because the name of this line is AB. So IAB is equal to IXX plus area into square of the distance between these two parallel lines. So this is IAB is equal to IXX. IXX is the moment of inertia of the area about its own centroidal axis along x-axis. So IAB is equal to IXX plus A area considered into the square of the distance y square. Similarly, the second parallel line is CD to the y-axis, and the distance between these two parallel lines is capital X. So now the moment of inertia about this CD line can be written as ICD is equal to IYY plus A into square of the distance between these two parallel lines. So ICD is equal to the moment of inertia of this area about y-axis, centroidal axis, and plus area multiplied by the square of the distance between these two parallel lines. So from these formulas or these relations, we can transfer the moment of inertia about any centroidal axis can be transferred to a parallel line to the centroidal axis only. So in this, this moment of inertia can be transferred to a parallel line about, to the centroidal axis along x-axis, and from this we can transfer the moment of inertia about this CD line, which is parallel to the centroidal axis along y-axis. Now area moment of inertia, by first principle. So number one, for rectangle. So suppose this is a rectangle. So this side of this rectangle is B, and this side of rectangle is H. This side of rectangle is B and this side of rectangle is H. So this is the These are the centroidal axis along x-axis and along y-axis, passing through the centroid. These are the centroidal axis passing through the centroid. Now, taking an elemental strip at distance y of thickness dy. Distance y of thickness dy, and the length of this strip is equal to d. Now, the area of this strip, area of this strip is dA. This is equal to d into dy. Now this is x-axis. So along this x-axis, the moment of inertia is represented by I-axis, and this will be equal to the integration of second moment of this elemental area about x-axis. So about x-axis, the distance is y of this elemental strip. So second moment of this area is equal to d into y square, and we will integrate it from here to here, from here to here. So it is at midpoint h by 2, because this is the centroidal axis, so it is at midpoint. So now we will take the limits from minus h by 2 to plus h by 2. H by 2 this side and h by 2 this side. So minus h by 2 to plus h by 2. So minus h by 2 to plus h by 2. So now, on putting the value of dA, limit is minus h by 2 to plus h by 2. On putting the value of dA is d into dy. So putting the value of dA, d into dy into y square, or equal to minus h by 2 to plus h by 2, or this is d into y square dy. So on integrating, v is constant, y cube by 3, and this is minus h by 2 to plus h by 2, or on putting the limits into it, b multiplied by putting the limits. So in place of y cube, h by 2 का whole cube minus h by 2 का whole cube divided by 3. So this will be equal to, on solving, this will be equal to b into this h cube by 8 minus this minus this minus on cube, this will be minus, so minus minus plus. So this will be h cube by 8 divided by 3. So on multiplying, adding and multiplying it, this will be bh cube by 12. So ix is bh cube by 12. And similarly, by taking vertical step, we can find out Iyy as h b cube by 12. So in this we can see that the cube of the side perpendicular to the axis about which we are determining the moment of inertia, because here we are determining the moment of inertia about x-axis and the perpendicular side of x-axis is h. So in formula, cube of the side which is perpendicular to the x-axis, and here cube of the side which is perpendicular to the y-axis. So here we are calculating moment of inertia about y-axis. So cube of the side perpendicular to the y-axis. Here we are calculating moment of inertia about x-axis. So cube of the side perpendicular to the x-axis. So always in calculating moment of inertia of a rectangle, the cube of the side perpendicular to the axis about which we are calculating moment of inertia. So this is moment of inertia about the centroidal axis. Now if in this rectangle, this is the centroidal axis and here it is the value ixx, this side is b and this is h. So this ixx is bh cube upon 12. bh cube upon 12. Now if we want to find out the moment of inertia about this line AB. So this is the centroidal axis. This is along x-axis. This is the centroidal axis along x-axis, and this is the line passing through the base. So it is at a distance h by 2. It is at a distance h by 2. Now by theorem of parallel axis, we can find out the value of IAB for a rectangle. So this rectangle is IXX plus area of this rectangle multiplied by the distance between the parallel line, its square. So IXX is bh cube by 12 as calculated earlier, plus area of this rectangle is b into h, and this is h square by 4. So this is bh cube by 12 and this is plus bh cube by 4. So on adding, this will be equal to 4 bh cube plus 12 bh cube upon 48, or this is 16 bh cube upon 48, and this will give you the value bh cube by 3. So this is about line passing through the base of the rectangle. This is line AB passing through the base of the rectangle. So this is centroidal axis, and we have transferred this moment of inertia about centroidal axis to the line parallel to it, like this. So by applying parallel axis theorem, this can be transferred to the line AB. Similarly, we can find out from this moment of inertia about AB, we can find out the value of moment of inertia I-axis on putting this IAB is equal to IXX plus A into H by 2 whole square. And if we know the value of IAB, then we can find out the value of IXX plus B into H into H square by 4. So BH cube upon 3 is equal to IXX plus BH cube upon 4, or IXX is equal to BH cube upon 3 minus BH cube upon 4, or this IXX is equal to BH cube upon 12. So by using parallel axis theorem, if we know that the moment of inertia about a line, then we can transfer it to the centroidal axis. We can find out the value of moment of inertia about the centroidal axis by using parallel axis theorem, like this. And if we know the moment of inertia about centroidal axis, then we can transfer it to a parallel line to it. So we can do by both methods by using the parallel axis theorem.